Now we'll consider the exponential distribution. So write it like this. X follows the exponential distribution with and has one parameter, which is lambda, which is the rate, the average rate. It has density function like this, and the mean. Here you have the lambda was a rate, so 1 over the rate is the mean. Yeah, we'll come back to what that means. And the variance is 1 over lambda squared. So you can calculate the mean and variance if you know lambda for an exponential distributed random variable. So the density function looks like this. It cannot be negative, and then it decreases as x gets higher. So it's more likely to get an outcome here close to 0. Yeah. So what can you use it for? It's a special case of the gamma distribution. Don't worry too much about that. You can study that later. But what we will use the exponential distribution for, what it's used for a lot in engineering and different application, is to describe lifespan. So if you have some component and you want to model how long time will that last, or you have some being and you can model how long will it live, then you can use such a distribution to model this. And also waiting times in a queue, for example, in some queue, the queue to this in the supermarket or on a server, if there's too much processes wanting CPU on a computer, then you can use exponential distributions to model these waiting times that you will obtain. Yeah, and what you can use it for is to model the waiting time in between Poisson events. So what's that? You remember the Poisson distribution? That was the one which calculated. So we had it last time. In the discrete. It's a discrete distribution, and you had a certain interval length, and then you would have the Poisson distribution would model the number of events in this interval, right? So every 2 minutes you will have 5 customers coming to your shop or something like that. The exponential distribution, if you have this phenomena, then the exponential distribution, it actually represents the time between the events, right? And what you need to think about is, if for example you have some radioactive medium, and you measure with this Geiger counter, and you measure these, so you have these blips of radiation, bling, bling, and actually inside this one there are billions of small molecules or atoms. I'm sorry, I don't know, but when they independently of each other, they sit there independently and choose. Now I'll send out some radiation, pling. And the other one sits and waits. At some point it says, now I'll send out some radiation. And if there's a lot of them and they do this independently, then you can model this. Then we call it a Poisson process. And if you count the number of events in an interval, then it follows the Poisson distribution. And the time between the counts, pling, pling, that follows an exponential distribution. Right, so for example, we can use it to describe some phenomena. Here, the time between customer arrivals at a post office is exponentially distributed with mean 2 minutes. So, in average, there are 2 minutes between the arrivals that a customer comes to the post office. Then we'll want to answer this question. One customer has just arrived. What is the probability that no other customers will arrive in the next period of 2 minutes? Okay, so we have just had an arrival, and so we'll write x follows an exponential distribution, so x will represent the time between the arrivals, and lambda here will be 2 minutes. And that's the first thing we'll write up. And yeah, that was wrong. I'm just going to delete it, and then x follows an exponential distribution. I'm sorry. With the parameter lambda, which is the rate, and we knew from a formula for the mean that the mean was equal to 1 over the rate, and so we can shift that around so that we get that the rate here is equal to 1 over the mean. Now it's correct. And the mean was 2 minutes, and we can think that was rate is a half per minute. That's the unit, right? All right. So what we want to calculate is the probability. We're asked to calculate what's the probability that no other customer will arrive within the next 2 minutes. That's actually that the waiting time is going to be above 2 minutes, right? And oops, we cannot look that one up, so we will say, oh, that's the same as 1 minus the probability to get that x will be less than or equal to, and that's equal to the probability of 1 minus or 1 minus the distribution function of 2 here, right? And then we'll go into R. Yes, let's calculate that. That was 1 minus the probability, that's the distribution function, capital F, of the exponential distribution, and then we said, what's the value? That was 2, and we need to give it the rate, yes, which was equal to 1 over 2, so a half. And so the probability is 36.7% that we have to wait more than 2 minutes before the next customer comes. So it's 7. We could calculate the same thing with the Poisson distribution. And what we need to do here is to consider this question again. A customer is just arrived. What's the probability that no other customer will arrive within the next 2 minutes? Okay, we need something related to 2 minutes intervals. Okay, then what we need is actually the 2-minute average rate. So that was the average rate for 2 minutes. We need that. And in order to get that, we say, oh, the rate here for 1 minute was actually a half. So if there arrives half per 1 minute, we will that will arrive 1 per 2 minutes. So we need to scale the rate with the length of the interval. So the 2-minute rate is 1. So we get 1 arrival in average per 2 minutes. And then the Poisson distributed value, now I just write it like this. Now we need to think about, now we need to think again. That's great, Peter. Yes. So now we need to think which probability is it then in the Poisson distribution. That's actually that we get no events in this 2 minutes interval. So the probability that the number of events, which is characterized by the Poisson distribution, The number of events is 0, that no one comes in the next 2 minutes. And yeah, we can calculate that. And there we would use the density function, because that was a discrete case, right? The density function of the Poisson that can give us exactly the probability of obtaining exactly this value, and that's the value 0. And here we need to give lambda, which is the lambda that we just calculated to 1, and then we get the same probability. So the point is that we can use either the exponential distribution or the Poisson distribution to get these probabilities, answering the same question, actually. So the answer is here. Yeah. Great.